After 25 years in the service business, it is realized you never see it all. A customer once called and explained that when she turned on the water in the kitchen sink, her doorbell would ring. Immediately, it was something that needed to be seen firsthand. Sure enough, she turned on the water and the chime went off. The initial thought was a possible grounding problem with the cold water bonding. The grounding system and the chime system were tested, but there was no luck. The next day, the customer was asked if the chime would ring when she turned on the cold water, the hot water, or both. She didn't know, so it was tested. It only rang when the hot water was on. It was asked if she'd recently had any plumbing work done, and it turned out she'd had the whole house repiped. The problem was then found in the attic. The new hot water line was laying across the front door button wiring. When the hot water was turned on and the pipe heated up, the connection was made. The plumber had slightly nicked the insulation on the bell wire during the pipe installation, but it only made contact between the two conductors when the hot water was turned on. This situation illustrates a unique and unusual electrical problem caused by an intentional contact between plumbing and low-voltage wiring. It highlights the importance of careful workmanship during installations and the potential for unexpected interactions between different building systems. Let's delve deeper into the factors at play in this scenario. Firstly, the doorbell circuit typically operates at a low voltage, often around 12 volts or 24 volts alternating current. This voltage is sufficient to activate the chime, but not typically dangerous under normal circumstances. Secondly, the hot water pipe, when heated, can become a conductor due to the mineral content in the water and the pipe material itself. While not as efficient as a copper wire, it can still carry a small amount of electrical current. Thirdly, the key element is the physical contact between the hot water pipe and the doorbell wiring. The plumber's accidental nick in the bell wire insulation created a point of vulnerability, allowing the pipe to energize the circuit when heated. Fourthly, the grounding system, while properly installed, did not prevent this particular fault because the contact was between the hot water pipe and the low voltage doorbell circuit, not a high voltage power circuit. The current flow was limited by the doorbell transformer and the resistance of the pipe. Fifthly, the process of elimination was crucial in diagnosing the problem. By testing the cold and hot water separately, it was determined that the issue was related to the hot water system. This narrowed down the search and led to the discovery of the physical contact in the attic. Sixthly, this situation underscores the need for coordination between different trades during construction and renovation projects. Plumbers and electricians should be aware of the potential for interference between their respective systems and take precautions to avoid such issues. Seventhly, the National Electrical Code, or NEC, provides guidelines for the proper installation and separation of electrical and plumbing systems. Although the doorbell circuit is low voltage, the principle of maintaining separation to prevent unintended contact still applies. The NEC Section 300.4 addresses protection against physical damage and requires that wiring be protected from damage during and after installation. Eighthly, in similar situations, several other factors could contribute to or complicate the problem. These include the type of pipe material, the quality of the water, the presence of other grounding paths, and the sensitivity of the doorbell chime. Ninthly, to prevent such issues, electricians should ensure that all wiring is properly insulated and protected from physical damage. Plumbers should be careful when working around electrical wiring and avoid making contact with it. Tenthly, homeowners can also play a role in preventing such problems by reporting any unusual electrical behavior, such as a doorbell ringing unexpectedly, to a qualified electrician. 11thly, in this specific case, the solution involves separating the hot water pipe from the doorbell wiring and repairing the nicked insulation on the bell wire. This eliminated the unintended electrical connection and restored the normal operation of the doorbell. This event shows that it is important to conduct thorough testing of electrical systems. You can test electrical systems by firstly visual inspection. Look for any obvious signs of damage, such as frayed wires, loose connections, or water damage. Secondly, use a multimeter to check voltage, current, and resistance in different parts of the circuit. This can help identify short circuits, open circuits, and other faults. Thirdly, perform insulation resistance tests to ensure that wiring is properly insulated and there are no leakage currents. Fourthly, test grounding systems to verify that they are properly connected and functioning correctly. Fifthly, use a circuit tracer to identify the path of electrical circuits and locate specific wires or components. Sixthly, conduct load testing to ensure that circuits can handle the expected amount of current without overheating or causing other problems. Seventhly, use thermal imaging to detect hotspots in electrical panels, wiring, or equipment, which can indicate loose connections or overloaded circuits. Eighthly, perform power quality analysis to identify voltage sags, surges, and harmonics that can damage electrical equipment. Ninthly, test ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or SIs, to ensure that they are functioning properly and providing protection against electrical shock and fire hazards. Tenthly, use a megameter to measure the insulation resistance of electrical equipment, such as motors and transformers. 11thly, conduct continuity testing to verify that circuits are complete and there are no open circuits. 12thly, use an oscilloscope to analyze the waveform of electrical signals and identify any distortions or abnormalities. 13thly, perform voltage drop tests to ensure that voltage levels are within acceptable limits throughout the circuit. 14thly, test surge protection devices, or SPDs, to ensure that they are functioning properly and providing protection against voltage surges. 15thly, use a clamp meter to measure current without having to disconnect the circuit. 16thly, conduct a thorough inspection of electrical panels to ensure that all components are properly labeled and in good condition. 17thly, perform a walkthrough of the facility to identify any potential electrical hazards and ensure that all safety measures are in place. The NEC addresses working on or near electrical equipment in Article 110. It outlines safety requirements for personnel working on or near electrical equipment, including the use of personal protective equipment, or PPE, and the establishment of safe work practices. Article 110.1 states that electrical equipment shall be installed and used in a neat and workmanlike manner. Article 110.3 covers examination, identification, installation, and use of equipment. Article 110.9 covers interrupting rating, stating that equipment intended to interrupt current at fault level shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Article 110.12 covers mechanical execution of work, stating that electrical equipment shall be installed in a neat and workmanlike manner. Unused openings in boxes, raceways, auxiliary gutters, cabinets, equipment cases, or housing shall be closed to afford protection substantially equivalent to the wall of the equipment. Article 110.13 covers mounting and cooling of equipment. Article 110.14 covers electrical connections, stating that because of different characteristics of the similar metals, devices such as pressure terminal connectors and soldering lugs shall be identified for the material of the conductor and shall be properly installed and used. Conductors of dissimilar metals shall not be intermixed in a terminal or splicing connector where physical contact occurs between the dissimilar materials. Article 110.16 covers arc flash hazard warning. Electrical equipment such as switchboards, panel boards, industrial control panels, meter socket enclosures, and motor control centers that are likely to require examination, adjustment, servicing, or maintenance while energized shall be field marked to warn qualified persons of potential arc flash hazards. The marking shall meet specific requirements. Article 110.21 covers marking. Equipment shall be marked with the manufacturer's name, trademark, or other descriptive marking by which the organization responsible for the product can be identified and to indicate performance characteristics. The marking shall be of sufficient durability to withstand the environment involved. Article 110.22 covers identification of disconnecting means. Each disconnecting mean shall be legibly marked to indicate its purpose unless located and arranged so the purpose is evident. The marking shall be of sufficient durability to withstand the environment involved. Article 110.24 covers available fault current. Service equipment in other than dwelling unit shall be legibly field marked with the maximum available fault current. The field marking shall include the date the fault current calculation was performed and be of sufficient durability to withstand the environment involved. The electrical safety requirements for safe work practices are covered by NFPA 70, Standard for Electrical Safety in the Workplace. The NFPA 70E provides detailed guidance on how to protect workers from electrical hazards. This guidance includes the use of personal protective equipment, the establishment of safe work practices, and the training of employees.